I work for CodeCentric. That's a company based in Germany. We do lots of Java, lots of consultancy, lots of big data, lots of different kinds of stuff. And I also do open source work, and mostly it's all in Clojure. And I do it in Clojure bags. Who knows what that is? So, who can say what exactly that is? That's the meaning of life, universe, and everything. But the problem is that it's an answer to the question of life, universe, and everything. But what's even the question? And it seems that somehow what we have in an analytics is exactly the answer, or like the 42, we have the 42, but we don't know the question. And numbers somehow evolve around percentiles, clustering evolves around words and spam filters. Well, if you take or open up like 4 books available on O'Reilly, which are mentioned in clustering in this or that way, all of them are going to explain you how to use well, clustering together with the, like TF-IDF, so it's basically word counts. And whenever you read about regressions, they are all about how to predict the page views. And no one even mentions the combinations, permutations of the things, or pivot tables, and so on. And basically that's a general schema of how the data science is being done. So we have something, I'm not allowed to really name it because I'm being videotaped. And then we have R, like the programming language of the choice, and we turn it into money. And I would like to say what reading 5 papers can yield for your business. And all these papers have been written, well, some of them like 20 years ago, some of them just several years ago. But still they give you some idea about the data that you can give in a with a very small memory footprint. And it's going to be about mostly minimal toolchain to yield some information. How to get the fields, like groups and permutations, how to get counts for categorical values, and distributions for numerical ones. And we, in order to do like some data science not according to the image that you have seen just now, you should have a good impression of the data. You should understand what it looks like. But somehow, whenever you start reading the books, everybody explains to you how to process the data or how to already crunch it, but no one explains you how to understand what even to crunch. So you should know how many. You should be able to ask your software, did you see that one? Like, did we already have the user with such an idea or by such an IP? What is the distribution of the numerical value? And how different are 2 vectors or, well, 2 values basically. And the last one is like, does it belong here? So I have, well, a set of round red ball, like red balls, and I have, well, a square, and I can ask my software whether my square belongs to the balls. So getting the info. And who's watched the talk by, I think it was Etsy guys, it was called Measure Everything. So, okay, not that many, surprisingly. Let's just say that you can efficiently measure locally and merge on the step machines. And, well, percentiles are cool and everything, but they're cool mostly for latency. But there are many more things that I consider more important than latency that you can/should measure in the application and business. And same approaches I'm going to be mentioning are used in the databases, in high-frequency trading software, in high-scale data analysis. So it should work pretty much for anyone. Who's heard about OLAP? Okay, that's cool. Every time you mention OLAP in the conversation, all the hipsters that OLAP, like, it's uncool. I'm higher than that, or I'm better than that. But the thing is that the principles of the OLAP, they are, well, eternal, kind of, in a way. And one of the first principles of OLAP is the consolidation. And in order to consolidate by time, you can use, for instance, tumbling windows. The tumbling window, for me, is kind of like a box. When we discussed it with the several people, we came to the conclusion that it looks like a monad, but just because the word itself represents like too many things at once for different people, I decided to remove it from the slide. So, for instance, we have a stream of integers, and the first integer we see is 1. So, whenever we open our tumbling window, we put 1 as an identifier, I'm sorry about that, and we wait until the difference between the number which is in the box and the number which is coming in the stream of data is going to be 5 or larger than 5, and then we close the window and move on. So we get 2 as the next value which is coming in the stream, and 1 is in the buffer, 2 is the next value, 2 minus 1 is 1, still less than 5. So we add 2 to the buffer, the next value is 3, 3 minus 1 is 2, still less than 5, then 4, 5, and eventually we get 6. 6 minus 1 is 5, so exactly it's the time to emit. So what we do right now, instead of 1, we put 6 in the box, and we'll start counting from the 6, and we're emitting all the values which we aggregated until that time down the stream. So that's kind of a tumbling window concept. And, well, it goes on and on, so we get a new buffer of only 6, then write 7 as the next incoming value, and accumulate until we meet the next value whose difference with 6 will be larger than 5. The next way to group by time is a sliding window. So sliding window also looks kind of like a box, and for instance we have a value of 1 which is coming into the stream, and we start computing until, or start accepting values into the buffer until we get a difference which is larger than 5. So 2 minus 1 is 1, and it's less than 5, and we start accumulating 2, 3, 4, 5, and we get 6, and since we got 6, we start dropping the values. So we emit the values from 1 to 5 that we got so far, and then we drop 1. We don't flush an entire buffer, so we drop 1 and append 6 instead. We drop 2 and append 7 instead, and that's a window that slides. So we don't drop all the values each time, but we drop a single value and append the next value, and that is very useful to see last n values, etc., etc. So grouping could also look like that. So you have a gender, height, weight, and number of occurrences, and you can say that, okay, we have 2 genders, male and female, and we have distribution of heights. Okay, we have a man of the height of 170 centimeters, and there are 15 occurrences of the weight of 73 kilos, like 28 of 75.5, and so on. So that's another way to group. And the joining is basically a Cartesian product of, well, 2 tables. And the thing is that whenever you are using the grouping, you can use, well, some standard aggregates. For instance, you can use count as an aggregate, or you can use sum as an aggregate. You can yield like standard deviation or median, mean, all the percentiles, and so on. But sometimes all these things don't yield enough useful information, and in these cases you can use things like count-min-sketch. Count-min-sketch is, an approximative data structure which is answering the question how many. For instance, you have a stream of data which is consisting from the several different colors. And you should get to know how many occurrences of each color there were in your stream. And the problem is that whenever you have like millions of IP addresses which are hitting your server, and you want to know how many requests there were per the IP address, in majority of cases you have to maintain the list of all the IP addresses that you have ever seen. You can imagine how expensive that could be, right? You can keep your Cassandra cluster or whatever the database of your preference just to store all the IP addresses with the numbers, right? Or you have the object allocations, for instance, in your Java or Scala program, and you want to count the number of objects which were allocated. So it is very efficient for the large amount of keys, for like very large amount of keys, and it gives you the approximation of the minimum amount of the occurrences of the given key in the, well, so far. In order to use count_min_catch, you are using the non-cryptographic hash function. For instance, murmur3 hash is, well, suiting very well. And we need n linear hashing functions to implement the algorithm, so we take a random seed. So it's basically calling, well, next random in Java. And the update looks pretty much like that. So basically you have k rows, and well, m is the width of the table, and we have in the end k, k seeds for the hashing function, and we start updating by, well, finding the hash from the incoming value, and for each of the seeds of the hash, we find the value which is matching like the vertical, or I mean the horizontal location, and increment it by 1. And whenever we need to look up the value, we just, well, pretty much do the same thing and find the minimum of the things that, well, where the arrows point. And that gives us an information about how many times at least the item has been seen in the stream of data. So in order to calculate, well, this is useful, you may say, but the problem is that in order to look something up, you have always to know the key, because technically count_min_catch doesn't hold you key with the amount of the occurrences, but rather it kind of distributes the key along all the, well, rows that you have by the hash functions, and therefore it is only useful to get to know whenever you have a key, how many times have we seen it so far. But that could be used to calculate a top k, so-called. For instance, you have like many IP addresses which are hitting your machines, and you would like to know which ones are the heavy hitters. Or you are selling the product, and on each sale, you can increment the counter, and that could, or top k could give you the list of the top selling products the same way. So in order to use the top k algo, you should just hold a count_min_catch in memory and do the update on each the event occurrence, whatever we have just seen previously on the slide, and do a lookup on the key in the count_min_catch and add looked up value to the top list. If the top list overflows, so it holds more values than, well, you have the slots available, well, because the list is sorted, you just drop the smallest value and continue the aggregation. And this way you will always be able to see well, for instance, 5 heavy hitters. There is also a stream in histogram, which is very useful to understand like the distribution of your data. The algorithm, or the update algorithm, is well described in the paper. I probably won't really go through it because I only only have 30 minutes instead of, I thought, kind of 45. So we kind of skip the... I mean, you can always look it up on the paper. It's anyways better described than on the slide. But the general concept is that you have the number or double numbers which are coming in as a stream. And you would like to know, okay, what is the distribution, like how the values are distributed. And whenever you append or you get a new value, you add it like to the very end. For instance, we got a value which was larger than every one of the ones that we have seen so far. So we add the one to, well, as the very last one. And after that, if we have more bins that we have planned, so the vertical things are the bins, we find the smallest bin, so the narrowest bin, and merge it with the next one. And, well, there is a formula to calculate how exactly you merge them. So basically, well, you get a sum of two bins, and this way you can maintain the histogram of the values, like how exactly they are distributed. And one of the examples, I have taken the database of the distribution of weights and heights and shoe size of the people, well, male and female, and that is how, like, what it looks like. For instance, that's the distribution of height. So there were 50 people whose height is in between 0 and 176, and there are, well, around 45 people whose height is like around 167, and well, etc., etc. So it's basically sorted by the decreasing amount of occurrences. So the least amount of the occurrences, as you can see, is of the people of around 189 centimeters high, and well, the largest is 176. The same thing with the weight. So the largest amount of the people which have been in the database I've taken were of around 73 kilograms. So it's like 45, 50 people, or well, a little bit more than 47 people, and so on. So the histogram is initially written for streaming decision trees. It will give you the exact stats, and it's very lightweight since you always keep only the n bins, and it's extremely useful when you don't know the value bounds. For instance, like with weight and height, we can kind of guess like how tall the people can get or how fat they could be. Technically, but there are cases when we can't really know the values. For instance, like whenever we are speaking about latency, or like even latency is predictable, but if we're talking about the prices, for instance, it's very hard to say like which bounds should we take for our histograms. For instance, if we are selling computers, it may be just like one range of numbers. If we're talking about human organs, it's a completely different thing. So HyperLogLog is another thing. I'm not going to go into the details, but you may know that it may help you with the cardinality estimation, so you will be able to count the amount of distinct items in the stream of data, for instance, and it's an approximate data structure, but you will always know the error. And having the ability to count the things, so basically you are able to get the list of the top hitters or heavy hitters, then you are able to get the histogram or the distributions of the numerical values, and then you're able to get, well, the histogram or the distributions of the categorical values. But now you may want to group your data in some way which you just don't know yet. So you basically want to cluster it. And in order to do that, you probably want to take your database or the logs that you had or whatever the data you have processed kind of offline and take something like a k-means algorithm, which will help you to understand, okay, which groups is my data, or can my data be separated to? And k-means works pretty much like that. So you have several points, and you define an amount k of the clusters you want to distribute, or you want to separate your data into. And well, the three color dots are one yellow, one kind of bluish, and third one is orange/red, are here. And so we basically place these dots randomly, and then we start optimizing, or so we split all the dots depending on how close they are to, well, the randomly chosen points. And then we optimize until we know that, okay, we have the minimum, or the dots are located, or are actually the minimum distance from the points, and we can converge, or we can't make it more optimal anymore. So it's like the best distribution we can get for this amount of points. And the problem with k-means, the one at least that I've mentioned or seen, is that in majority of cases people are describing it not with the vectors of values, but rather they are, well, they almost never operate on double values, rather they always operate on key value hashes, kind of, and which represent the term frequencies. For instance, they say, okay, we can do the filter or cluster the books to different subjects or whatever else. So I would say that it's way more useful if you use k-means implementation that can work with the double vectors, because this way you can represent any data set that you can possibly imagine as a vector of doubles, and then cluster these doubles. And, well, get the pretty pictures which will tell you the story that you haven't known until today. And the last thing I'd like to mention is the naive bias, which is kind of, for me, working together with the k-means algorithm. And you can use the Bayesian algorithm with the observation that you yielded through the k-means in order to identify the whether the new data points that are coming to your system are belonging to one of the clusters that you have identified. And well, once again, make sure that your Bayesian algorithm operates on the vectors of doubles, and well, it basically takes a model which is variance in the cluster mean, and finds the cluster which is well, closest to the observation. Okay.
Go back a slide and start again.
Yeah, probably I should do that. No, I don't want to bore you to death. Actually, the thing is that I've mentioned the algorithm that can help you counting things in the predictably large space. I've mentioned something that can help you to build histograms of the data also with a fixed space. And in my opinion, with just these two things, you can already gather such an amount of information that was, at least for me, unimaginable before. I unfortunately cannot really mention what exactly we're using all these things for, but the only thing I can say is that it's never been possible for us to measure so many things at once. For instance, databases like Elasticsearch or Cassandra, they're using also Bloom filters, but well, streaming histogram are also used in Cassandra. And I know that some of people use in the database world also the count-min sketches, and people like Google are using them to identify the header hitters and so on. So if you use these approaches, you can count an unimaginably large amount of things. And the more you count and the more patterns you're trying to find. For instance, you would like to know how many things or how often the latency on my application is getting larger than a particular value. And before that, you should have like logged your thing to the statsd or whatever, written it to HDFS and so on. But like what you can do with these things, you can just maintain a very lightweight data structure, and you can know or be absolutely sure that there's been a minimum of a certain amount of occurrences in the data stream. And you can maintain the list for, well, quite a long amount of time, and then, well, yield the results which would have been much more difficult for you to yield beforehand. And you don't have to have a Hadoop cluster. You don't have to set up anything. All these things are implementable in maybe 20 up to 40 minutes of your time. And actually that's very interesting too. So I would say that having an idea about the algorithms which help you to yield the info from the data in the predictable space is a very promising thing, and is going to get bigger and bigger like every day. And I highly advise you to check out all those papers that I mentioned today. And that's it.
We have time for questions.
Yeah, we have time for questions. That's good. Yeah.
Just, if I don't understand, just correct me. Is the CM, sorry.
Conman sketch, yeah.
Is that like a Bloomfield which you can count the occurrences that you've had, and you would get like a set of values, and you would take the minimum to know how many occurrences that was?
Okay. Let's. Probably I should have taken even more time for the question, or.
Because it seems pretty like useful.
Okay. So basically, for instance, you have an IP address. IP address in this given example is an I, and by the vertical axis, the K, like every line or row is think of it as a hash function. More3 hash with a random seed, right? So basically, for instance, you have the IP address of 1.1.1.1 somehow, okay? And you take a hash, it's like 344, and the M is, let's say, 20. You take a modulo of 344 modulo 20, and you get, for instance, number 3. So, and you increment by 1 the third, so first and third, so first line, third column, and that's going to be a minimum of okay, then you do it for each of the hashes, and whenever you do the lookup, you find the minimum of these things, and it's going to be the minimum amount of times that this item have been seen in the stream. So most likely the item have been seen more times, but that is the least number that is possible to predict.
Thank you.
Yep.
Could you just give me the name of the paper that you used for streaming histogram that can be used for streaming decision trees?
It's basically streaming histograms for, or it's basically called streaming decision trees, but it's whenever I upload slides, I make sure to mention all of them, and I will just tweet or whatever.
When you categorize the unknown data that you don't know before with k-means cluster, you have to somehow decide what the k is, right? The number of clusters. How do you do it?
Usually, you start with some small number. Well, at least if you know that amount of the categories is gonna be, well, relatively small, like 5 for instance, and if you see that it's too much, then you decrease it. If you see it's too little, you increase it. But as I mentioned, the thing is that the way, at least we've been trying to do that, is we never were ending up with like 40 gigabytes or 40 terabytes of data that we have to process. So in majority of cases, we just had to query our like lightweight data structures and yield some reasonable data from them, rather than have a Hadoop cluster just well, crunching the numbers and, well, then generating the k-means, then, well, we have to, well, wait for 1 week just to get even the basic results. So the more lightweight things you use, the more you can experiment, and the more freedom you have, the less you should wait, and the more creativity you can have in your like data analysis process. But like all the data should be on top of your fingers. It should take like less than a second for you to get pretty much any response. It's like that's why many people at their time decided to use iPhones, not Android phones, because like Android phones always had that little lag. Not anymore though, but you remember the times here.
Question? All right. Thank you very much.
Yeah, thank you. Yeah, it's okay.